The content of section 1.8 deals with polynomial equations. We'll talk first about the standard form approach. Any nth degree polynomial equation should always be started in standard form, meaning I'm going to move all of my terms to the left-hand side so that I have a right-hand side of 0. Again, the easiest way to think about this is that it's a default starting position so that we can more easily use other techniques. First degree polynomials are linear equations, which is what we saw in section 1.7. Second degree polynomials are called quadratic equations, which will be the majority of our focus. And third and higher degree polynomials are only going to work if the GCF method of factoring works, or we can rely on second degree polynomial strategies. But there's not necessarily a guaranteed strategy for third and higher degree polynomials. So we really just care about the quadratic kind in this section. So about this standard form default starting position. This is just a convention. It's always a good starting strategy so that we can employ other strategies when needed. So if I have the polynomial equation 3x squared equals 4x plus 13, I'm going to first move every term to the left-hand side so that I have a right-hand side of 0, as I've done here. 3x squared equals 4x plus 13 becomes 3x squared minus 4x minus 13 equals to 0. And we can do the same thing with this second example. 2x squared minus 3 equals 3x minus 3x squared will become 5x squared minus 3x minus 3 equals 0. A lot of our solving techniques will really regard what the coefficients in standard form of our polynomials are. In that first equation, I had a positive 4x on the right-hand side, which became a negative 4x on the left-hand side. So it's important to get everything to the left-hand side so that I know the signs of all the coefficients. It also shows us a simplified version of our equation, because that second example had an x squared term on the left and the right-hand side, and this did need to be simplified. But why is the right-hand side of 0 important? We're going to use something known as the zero product property, which says that if a times b equals to 0, then either a or b has to be equal to 0. Obviously, we know that 0 multiplied by anything gives me 0. So if I have a product of two things that equals to 0, it means that one or the other, or both, was 0 in their own right. This is going to be a very powerful property for us. The standard form quadratic equations above are written as a sum or difference of a bunch of terms. We want to see if we can use factoring methods to express the left-hand side as a product instead of a sum or difference. This will allow us to use the zero product property. Let's look at an example that works with the GCF method. Consider the equation 10x squared equals to 5x. Let's first move this into standard form and subtract that 5x from both sides. This gives me 10x squared minus 5x is equal to 0. I notice that I have a greatest common factor of 5x, so I can factor that out and write this now as a product, 5x times 2x minus 1. So a couple of things to notice. Each factor in the right-hand side is a linear factor, and we saw from section 1.7 that linear equations don't take too much effort to solve. And since my right-hand side is 0, I get to use the zero product property. So to do this, I'm going to split my left-hand side into two separate equations. 5x equals to 0 and 2x minus 1 equals to 0. Again, the reasoning behind this is as follows. If 5x times the quantity 2x minus 1 is equal to 0, then either one or the other needs to be 0. So the mentality here is that we started with one big equation and we ended up with two smaller equations, and solving these will give me the solutions. Solving these two equations is pretty straightforward. We'll find that 5x equal to 0 gives me a solution of x equals 0, and 2x minus 1 equals to 0 gives me a solution of x equals to 1/2. The easiest way to check our work is to plug these values back into the original equation and see if we get a true statement. 0 clearly works, but if I plug in 1/2, we also get a true equation. So to summarize what we just did, we wrote it in standard form, we factored out the GCF, and then we used the zero product property, and we're done. But we saw in the last section that not every polynomial factors with the GCF method. Let's try to do some problems that use the AC method. Take the equation x squared equals to 7x plus 30 and then write it in standard form. We'll see that we have no greatest common factor, but this does factor as a quadratic. Since the number negative 30 factors as negative 10 times 3 and negative 10 plus 3 equals negative 7, I have the numbers that I need to match with my coefficients. This is going to factor as the polynomial x minus 10 times x minus 3. So even though I can't use the GCF method to factor polynomials in every case, I can sometimes factor a polynomial using the AC method. This still lets me use my zero product property like I want. my left-hand side is a product of things, my right-hand side is 0, so I can set each individual factor equal to 0. So I get the two equations, x minus 10 equals to 0 and x minus 3 equals to 0. I've gone from a quadratic equation, in other words a degree 2 polynomial equation, to two smaller linear equations. And we're seeing that linear equations are typically the simplest kind of equation that we can solve. Because the two equations I have here can be solved by adding a 10 to both sides or adding a 3 to both sides. In other words, they take relatively simple actions to isolate our x variable. So what we're going to get is the two solutions of x equals to 10 and x equals to 3, and we're done. So again, the whole point is to see if your polynomial factors somehow, either by AC method or by factoring out the GCF. Let's look at another example. Take the polynomial 2x squared plus 8x minus 4 is equal to 6. First, I need to reduce it to standard form, which means I need to subtract a 6x from both sides. This will give me a 2x squared plus 2x minus 4 is equal to 0. This polynomial requires the AC method to factor, but we can see that standard form is really important here. On the left-hand side, I originally had an 8x, and on the right-hand side, I had a 6x. So trying to figure out the b coefficient for the AC method would have been hard because is it an 8? Is it a 6? We don't really know. That's why we need to subtract everything over to the left-hand side and write it in standard form so we know what our actual coefficients are. We've seen that the AC method heavily relies on the coefficients and the sign of those coefficients. But now that this is in standard form, we know that a is equal to 2, b is equal to 2, and c is equal to 4. So we'll draw our cross and put -8 and 2 in the north and south slots respectively. And then by a little bit of guesswork, we'll see that the numbers -2 and +4 are going to work for us. -2 times +4 gives me -8, and -2 times +4 gives me 2 as desired. The factor by grouping details are posted in the notes, but we're going to get the factorization of x minus 1 times 2x plus 4. Right now the posture of this equation is good because I have a product on the left-hand side and 0 on the right. This means I can split it into two linear equations, x minus 1 equals to 0 and 2x plus 4 equals to 0. And the solutions to these equations are going to be x equals to 1 and x equals to -2. So the main idea is that if I have a quadratic equation where that quadratic is factorable, either by GCF method or by AC method, then I can factor that polynomial and use the zero product property to give me two linear equations that are easy to solve. And this is how you solve a quadratic equation for a factorable polynomial. In our next example, we're going to turn up the heat a little bit and look at what we call a quadratic-like equation. So consider x squared plus 2x quantity squared minus 7 times x squared plus 2x minus 8 equals to 0. This isn't very nice to look at because if I started foiling out these terms, I would have terms like x to the 4th and x to the 3rd and so on, and it would be kind of a mess. But what I want us to notice is that I see the term x squared plus 2x written in two places. And that first one is risen to the second power. So this resembles a quadratic equation. What we're going to do for the sake of this thing called U-Substitution is take that repeating term and assign it the letter u. In other words, I'm going to let u stand for the expression 2x squared plus 2x. You can think of it like u for ugly. But whenever I replace x squared plus 2x with the letter u, I get the new equation u squared minus 7u minus 8 equals to 0, which is objectively a lot nicer to look at. This is essentially the mathematical equivalent of put it on the back burner. That expression x squared plus 2x, which shows up twice, is just something that we'll deal later. We put it in a box right now that we're calling u, and now we're going to solve this equation for the variable u. It's very common to refer to variables like u in this case as a dummy variable. It's just something that we're using as a sort of placeholder so that we can get back to it later. But right now the game is to solve for u. The equation that I have right now, u squared minus 7u minus 8 equals to 0, is factorable. We're going to factor the left-hand side as u minus 8 times u plus 1. -8 times positive 1 multiplies to -8, and then they sum to -7, so these coefficients work. The zero product property says that I get two equations, u minus 8 equals to 0 and u plus 1 equals to 0. And these are going to give me solutions of u equals to 8 and u equals to -1. So are the solutions to this whole equation -1 and 8? Not quite. We're not actually done. We've solved for u, but we haven't solved for x yet. So that term x squared plus 2x has been on the back burner, now we need to bring it forward. I now have the equations u equals to -1 and u equals to +8. So I'm going to set up the equations x squared plus 2x equals to 8 and x squared plus 2x equals to -1. So what I've got now is two different quadratic equations that I need to write in standard form. This will give me x squared plus 2x minus 8 equals to 0, which factors as x plus 4 times x minus 2 equals to 0. Next, we've got the equation x squared plus 2x plus 1 equals to 0, which factors as x plus 1 times x plus 1 equals to 0. Then by using the zero product property, we get a final set of solutions of -4, -1, and +2, and we're done. So the whole idea of U-substitution is to take something that looks like a quadratic and set up a dummy variable that we call u. We first solve for u, and once we have u isolated, we replace it back with what it originally stood for and then solve for x. In our next video, we're going to talk about how to deal with equations that don't factor.